Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 27th instalment in CompBioMed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. The talk today will be given by Dr. Alia Arabi, Associate Professor for the Department of Biochemistry in the College of Medicine and Health Sciences at United Arab Emirates University. Since 2017, she's also been an honorary lecturer in the Department of Chemistry at University College London. Her research concerns the investigation of biochemical systems using computational tools, and in particular, she has studied the effect of external factors on mutations in DNA, which is the subject of today's talk. Now, before we begin, I'd like to briefly remind you that the session is being recorded and will be available on the CompBioMed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There'll be a Q&A session at the end of the talk, so please save your questions until then. Once the talk is finished, you can go ahead and post your questions in the Ask the Staff a Questions panel, which should be accessible via the question mark icon on your screen, and I will read them out to Alia to keep the session running smoothly. Now that's enough from me. I very much hope that you enjoyed today's talk. And finally, Alia, please feel free to take it away.
Hello, everyone. Thank you, Tim, for the introduction, and thanks to CompBioMed for arranging these seminars. Am I being clear with my voice?
Yes, loud and clear.
Okay. So before I start my presentation, I just wanted to share with you a picture of our main campus in the UAE. And this is in Al Ain city, which is driving distance is about 1 hour and 20 minutes away from Dubai. So let me get started with the science. I'm here today to tell you about point mutations in DNA, and I will tell you about how we are building a model to estimate and evaluate these point mutations in DNA. In the model, I'll go through the details of the molecular dynamics, the quantum mechanics, and the QMMM model. And then I will tell you what was the effect of these point mutations that we observed in the GC base pair and the AT base pairs in the absence of electric fields and in the presence of electric fields. And then I will tell you about the biological implications of these things and wrap with conclusions. So to begin with, what are point mutations in DNA in the context of Löwdin mechanism, and why we are interested in looking at them? So Löwdin is a scientist who suggested that mutations in DNA are occurring as a result of the following process that I will talk about, and he calls them as point mutations. So in DNA base pair, we have hydrogen bonded GCs and AT, and you can see that as we do have a replication, the DNA will unwind. But upon unwinding, you can have here the hydrogen bonding start to break between the base pairs. If they were to break properly, and here I'm showing an example of the AT, the A will go in one side and it's free to complement with freely available thymine, and they will have beautiful complementarity. Similarly here for the thymine, you will have the thymine and it will collect a freely available adenine, and they complement nicely. However, during the opening here upon replication, it is possible that this H would exist on that side, and as a result, this H should be here on this side. And that is as a result of something we call it double proton transfer. And this double proton transfer will result in having rare tautomers. So instead of having adenine, we will have adenine star. And if it were to collect a freely available thymine, they will not hydrogen bond anymore because there is here a clash. Similarly, for the thymine, it will go to the rare tautomer of thymine star, and this thymine star does not complement with the adenine as it's supposed to do with the regular thymine. So here, if we look at the example of the GC that had tautomerized to the rare tautomer G star C star, upon the first replication, a C star will be formed and it will go complement with an A, and the G star will go and complement with a T. Now, upon the second replication, the A will go and complement with a T, and the T will complement with another A. So starting with a GC base pair, after 2 replications, instead of having all GCs, we created 50% of GC, but also the other 2 were 80. And this is known as the bias toward the GC being converted to 80. And this has been observed experimentally with X-ray crystallography. And the mutations that happen there are at the rate of the observed spontaneous mutations per given genome are up to 30 base pairs of mutated points. Then we were interested to see, okay, according to this Löwdin mechanism, which says there is the tautomerization that's causing point mutations, we really want to understand how is this happening? Why is it happening? And not only this, we want to take it one step further by seeing all of this phenomenon, how does it change when we apply electric fields, in the hope that one way or another we can use these fields to fix the mutations that are occurring. But first of all, we want to see if they cause any of important changes to begin with. As a first step of this study, we really had no clue where to start from. And we just really needed to have an absolutely simplified model that has cyclic double proton transfer, where this proton moves here and this one moves there. And this is the formic acid dimer. So we would just use the system here to decide on the force on the electric field strength, to decide on which ones are important, which ones are not, and how the thermodynamics and kinetics change. But I will not get you into the details of the result of this, because then we move to applying the same study on the AT base pair. And here in the AT, we have the hydrogen 4 moving to there and the hydrogen 7 moving right. And similarly, we applied the study on the GC base pair as well. And in the GC base pair, because we have 3 hydrogen bonds, you can see that the double proton transfer can happen for the H4 and H8. H4 and H9, but also H8 and H9. And we studied all 3 of them, and we found that only this one is the most important one that shows any relevant results. And all of these 3 studies have been done at only using QM method for this single system that we are seeing in the gas phase. So we wanted to move on to a realistic model of the DNA and see how the results will be changed, because we want something that can be of applications in medicine eventually. So we built a multiscale model, and in this multiscale model, you can see that we started with a dodecamer here of DNA, and we did the counter ions and solvation. Then we moved it, and we selected out of these MD simulations 24 snapshots, and we simulated all the 24 snapshots through QMMM simulations, where the QM is the base pair of interest, and the rest of the system up to a certain region is in the MM, and the rest is frozen. And you can see here in the QM region, we are taking the base pairs where we are looking at the double proton transfer, or in some cases, single proton transfer tautomerizations. So to begin with, what did we do with the MD simulations? We used MD for MD and with the Amber force fields. And we started with PDB ID, that's 1 BNA for a dodecamer of DNA. We neutralized it with sodium ions and solvated it using the TIP3P model. And then we thermalized it at 300 Kelvin. But we were not happy with only running one simulation, because in molecular dynamics, as most of you know, that if you have a given structure, the trajectory that it follows depends on the initial velocity. So it could go and traject end with this product or this product or this or that. And we wanted to kind of cover as wide of a spectrum as we can. So we did 10 replicas, 10 nanoseconds each, and we selected 10,000 frames out of these replicas, from which we chose 24 frames to do on them QMMM. So for the QM model, what did we do? We used NWChem, and we had a wide variety of methods we could use. So we decided to do a benchmark of the studies to make sure, of the methods, to make sure that we are selecting one that is properly capturing the energy that we want here. for that, we took some DFT methods, but we also took wave function methods. And these are the list here. And for the DFT method, we complemented them with dispersion corrections, D3, D3BJ, and the exchange hole dipole moment. And we tested the model on both Pople basis set and Dunning basis set using double zeta and triple zeta basis sets. So all of these are variables within the QM region that you can play with to make the method as accurate as possible, to make sure that you are getting good results that you are hoping for with the biological implications. The energies that we got from all of these combination of methods were compared to a golden standard couple cluster at a complete base set limit from Hopsha's study. So here we did some, I'm showing you the results with respect to energy and geometry, and here you are seeing the errors. And this is on a system that's hydrogen bonded, the GC. And you can see that some of the methods are giving really low errors in energy, but in geometry, they are kind of higher. But there are these here, the B3-lip XDM is giving a good combination of low errors in energy and geometry, more specifically with the augmented Dunning basis set. Now we were happy with the hydrogen bonding. We then moved to studying also the stacking interaction, which are really, really weak interactions. And we want to make sure that also our methods are catching them. And for that, we took a stacked base pair. For example, it could be GC-GC, but we took a set of 10 of them. And we calculated the energy of stacking, which included not only the intra between this and that, for example, or this and that, but also the inter-diagonal interactions. And with this, these are the results here. And you can see that we are highlighting the lowest errors that happen to be with the B3-lip plus XDM with augmented Dunning basis set at the double zeta. Now we just wanted to make sure about the sensitivity of the end result of QM with respect to slight changes and modifications of the initial structure to begin with. And we saw it to be kind of really insensitive in a sense that we had RMSEs in the geometries that are less than 0.02 angstrom, and we were happy with that. As a result, we decided on using B3-lip XDM with Dunning double zeta augmented basis set. How did we build our QMMM model? We used ChemShell with the DL-find module to link the NWChem with the, which is for the QM region, with the MM region for using DL-poly. And here, what we did is we chose only one base pair in the QM region, and we relaxed around the region around it, with including almost 9,000 atoms, which was around 6 base pairs here were in the QM region, while the rest was frozen. The reason why we chose, so here you can see from the center of the system, we went away with about 15 angstroms. Now, why did we choose one base pair is something that I will talk about. But before that, I want to tell you that this number of 24 replicas that I told you we are using as snapshots to start our QMMM calculations is not a magic number. We did some error analysis with the energy, and we saw that if we do only one simulation, this is the error. If we do 2, 3, 4, 5, you can see that the error starts to level off. And we were happy with the choice of 24 replicas. In some cases, we did even 25 replicas. So here I'm showing you the bootstrap analysis, showing you basically the same concept as to where the error levels off. And we are happy with the choice of 24 replicas of QMMM simulations. Now, as I mentioned earlier, we did 10 MD simulations to begin with at 10 nanoseconds each, so a total of 100 nanoseconds. And out of this total of 100 nanoseconds, we collected 10,000 snapshots. Now, how did we reduce these 10,000 to only 24? What we did is in each of the 10,000, we looked at the distances between the hydrogen bonds in the base pairs. And we did this distribution, the normal distribution, to find that this is the most probable distance that we found. We did plus or minus a little bit to cover up to 24 geometries at this value. So for the QMMM, we solvated, of course, the model here with the water. And after we optimized for the transition state, the reactant, and the product, we did generate the intrinsic reaction coordinates. Basically, we generated from here, we asked the reaction to go down to show us how it would prefer to go through the process. In other words, it guides us through the mechanism of how it's happening. So with this, we did the nudge elastic band to compute the IRCs, and we made sure that our transition states are transition states by looking at the imaginary frequencies and making sure that we have one and only one imaginary frequencies. Then we, as mentioned, we took only one base pair in the QM region for the following reason here. You can see here we are doing kind of a benchmark study where in blue, you see that for the QM region, we took 3 base pairs, and for the MM, we took 5. Then in the rest of these, we took in all of them only 1 base pair in the QM region, and we increased the MM region from 3 to 5 to 7. And what we noticed was that if we look at the energy difference from reactants to the first transition state, for the 3 base pairs in the QM region, we didn't find much of a difference compared to the one base pair. And this error actually was within the error margin that we found for having the ensemble of multiple QMMMs. So we were happy with deciding on only 1 base pair in the QM region. Okay, then let's get into the results of what we found in the absence of the electric fields. First, we started with having the reactant, which is in its canonical form. I'm showing here the GC, but it applies equally for the AT. And then we looked at the products. The products, we had 2 forms of products. One of them is a Zwitter ion, G minus C plus, which happened as a result of only 1 proton moving. So here it's a single proton transfer that's leaving us with a Zwitter ion plus and minus complex. And we looked at the double proton transfer product, which is a rare tautomer, G star, C star. And here it comes as a result of double proton transfer with 2 protons moving around. So for the single proton transfer, we have 1 option and 1 reaction, and we didn't see anything else for that. So that was it, 1 transition state, and the reaction happened with a motion of 1 proton, it was done. However, for the double proton transfer, we observed 2 mechanisms. One of them is concerted, where we saw only 1 transition state, and the reaction happens in 1 step. But the other one is a stepwise mechanism, where you can see here, you have 2 bumps with 2 transition states. Starting from the reactants, you have to go over both before you can go to the product. Basically here in the concerted, you're having both protons moving at the same time to make the transition state and reach the product. In the stepwise, you have 1 proton moving first and then the second one follows it. And this is why you have 2 steps. These are the results that we saw for the 25 replicas. What I would like you to observe here is that for the majority, here we are looking at the GC. For the majority of the cases, you see the double hump, meaning that in most cases it preferred the stepwise mechanism, meaning that for sure it was a double proton transfer that is preferred in most cases. However, if you look here at the AT results, you see a lot of blank because in many of the occasions, the reaction did not want to go. And what I mean by this, I will show you in another few slides. So the reaction did not want to happen. And if it were to happen, it would happen only with 1 transition state, which after examining the product, we realized that it's a single proton transfer with the formation of Zwitter ions. So just to give you statistics of what we found overall, for the GC base pair, we found for the concerted only 12% of the times to happen. For the stepwise, which was the favored one, 84% of the times it happens. We only saw 4% of the times a single proton transfer with the GC, and in none of the times did the GC not want to react. For the AT, we saw that it just does not want to do double proton transfer at all, whether it was versus concerted via concerted or stepwise mechanisms. And you can see that 30% of the cases are happening with the formation of the A plus T minus Zwitter ion through a concerted single proton transfer. And for 70% of the times, it just did not want to react. And we found only one occasion of a rearrangement. Okay, so in the results, what is it that we were looking into observing in particular? First of all, we wanted to look at the thermodynamics and stabilities of the systems. And for that, we started with the electronic energy, and you will see that I will be reporting these electronic energies, but we had also added some corrections to them, including vibrational and zero-point vibrational energy corrections, and that formed the E-corrected. But for the E-corrected, we also took into account the temperature and the entropy factor to compute the Gibbs energy. So you'll see I'll be reporting electronic and Gibbs energies. The other thing we wanted to look at was kinetics. We want to see how fast the process is happening. And for this, we calculated the rate coefficients with the very conventional, it's the conventional transition state theory. And you can see here that the rate is equal to this very standard format. And here we are adding a correction term. And this correction term accounts for something called quantum tunneling. This correction term can be approximated with various models, but we decided on the Wigner tunneling correction approximation based on the results that we found from our prior studies. And in this Wigner correction, you see that it's basically constants, but you have here Planck's constant. You have this here, which is the imaginary frequency at the transition state. And you have this beta, which is also a constant 1 over Boltzmann constant multiplied by the factor of temperature. Then we moved into calculating the equilibrium constant of the whole process. And for this, we just had to take the ratio of the rate that we calculated for the forward reaction over the rate of the reverse reaction. And then we were ready to calculate the half-lives as shown here. And you will see that at some points I will report concentrations of the products at a given time, t. So at a given time t, I can calculate how much of the product I have produced. And this is a simple equation that basically depends only on Kf and Kr, which I'm calculating from here. So what did we find for the GC base pair? Here I'm showing you the average energies with the energy profile for the stepwise mechanism where you have the two transition states, and it occurred 84% of the times, and also for the concerted mechanism that happened 12% of the times. And you can see for the concerted mechanism, the barrier height here is higher by almost 2 kcal per mole, and that could basically explain why that mechanism was not as favored as this one, statistically. The other observation to make here is that when we are looking at the red line versus the blue line, the blue is electronic energy and the red is Gibbs. So you can see that the red here with the Gibbs, everything is kind of flattened. It happens in both scenarios. And here you can observe for this stepwise mechanism that the product is reinforced in terms of instability, and therefore it was wishing more to return back to its canonical form. And this is why we are confident to claim that DNA is trying to keep its fidelity, that even if we were to form this GC star, rare tautomer, it would want to return back to its canonical form. For the rates, we had to dissect the energy profile into two parts. And in the first part here, you can see that we are looking at the rates forward, but also the rate reverse. And the rates depend on the barriers. The higher the barrier, the slower the rate of the reaction to happen. And you can see here that the barrier here is much higher than this one. And this is why you can see that the forward rates are much slower than the reverse rates, which are shown here in much higher. So here I'm showing you the probability distribution of all the rates that we had calculated across the 24 replicas. And you can notice here that the K forward is 10 to the 8 times less than the K reverse, meaning that it's a lot slower. Now, if we look at the K equilibrium of this process for the first step, you can see that it's equal to the 10 to the minus 8, which is way less than 1. meaning that the reaction would prefer to go back. It's going back thermodynamically favored, and it's going back at a fast rate. Let's see what happens in the second part of the reaction. You can see that the barrier heights are almost equal here, and therefore the forward and reverse rates are almost equal. And this is why you see here a big overlap region between them. And you can see that after calculating the K equilibrium, it turns out to be almost equal to 1, which says that this process here is almost at equilibrium at all times. Now, to compare with the experimental data, here for the stepwise mechanism, we see for the forward, it was 10 to the 6 per second. For the K forward in the concerted, it's 10 to the 5 per second. Experimentally, it was 10 to the 5. So we were happy with this comparison. If you look at the rates of the reverse, we are moving to 10 to the 13 and 12. So it's a lot faster. It moves a lot faster backwards than forward. And not only this, but also we looked at the stability of the products that are formed by evaluating their half-lives. And you can see that these are absolutely not stable. They only live for 20 femtoseconds. These ones live here for 3 picoseconds, which is kind of expected because the reverse barrier is a little higher than the reverse barrier here. Okay, so what did we then see for the AT base pair? We found the following, and you see when the blue again is the electronic energy and the red is Gibbs. So when we look at the electronic energy, it looks fine where the transition state is higher in energy than the product. However, when we correct for the rest of the terms and calculate Gibbs energy, we notice that the product is higher in energy than the transition state. And we know that this is a transition state because we confirmed it by the imaginary frequency. So there is something here that doesn't make sense, and to have a product that's higher than the reactant in energy. And here we hypothesize that it's one of two scenarios. Either the AT just does not want to do the tautomerization at all, and this is the thing that we have seen earlier when I told you it was mostly blank and the reaction does not want to take place. And that was almost 70% of the cases. Or if it were to happen, it will happen quantum mechanically through tunneling only. So there is no barrier overcoming. So this is the story with the AT. It doesn't want to form the rare tautomers. If at all it was forming a Zwitter ion. So you can see most all of those were through single proton transfer. We had 0 reported for the double proton transfer. You can see for the K equilibrium, it's also less than 1. So the reaction, as soon as it forms the Zwitter ion, it wants to return back to the canonical form. And you can see that the half-lives are 6 femtoseconds, absolutely small period of time. They are very unstable. They really want to return back. And if we look at the rates, you see that the rate for reverting back is very fast, as opposed to the rate to move forward is even very scattered, and you cannot, it happens very slowly. Here I'm showing you the concentrations. How much of GC star have we formed after a given amount of time, and how much of AT Zwitter ion have we formed after a certain amount of time. And you can see that for the GC rare tautomer, it takes about 10 to the minus 10 seconds before it reaches equilibrium and stabilizes, as opposed here, it's about 10 to the minus 13, which is a lot faster and before it stabilizes. Okay, the other thing to observe is for the Zwitter ion here, it is forming at a lot higher percentage than the G tautomer. And you can see here all the numbers in percent are in micro, as opposed here it's only times 10 to the minus 1. So in other words, for the Zwitter ion, after a certain amount of time, I'm generating 0.06% of them out of the entire genome of AT base pairs. And here I'm only generating 0.8 micropercent of GC star tautomers compared with the full amount of GCs in the whole genome. So here I'm summarizing these results. So after 1 second of time, we have 8 Zwitter ions of the GC. 12 rare tautomers of the GC, and almost 100,000 Zwitter ion of AT. A huge amount, much more formed for the AT Zwitter ion than these two. So this is accounting for 0.06% of the whole genome. Now, assuming that the genome is made out of 50-50% equal amounts of GC and AT, and assuming for a permanent mutation, you need a reverse barrier that's greater than 3 kcal per mole, and taken into consideration that the DNA opening replication is 1 billion times slower than the half-life of the rare tautomer, which is in the scale of picoseconds, we conclude that less than 1 base pair out of these 12 that are formed for the GC will actually remain permanently mutated in the genome. How does this compare with what I showed you originally? Originally, we said there are 30. But are we sure that all 30 are as a result of the Löwdin mechanism? No, there are other things. So here, only one of them is coming from the Löwdin mechanism, and the rest are as a result of other things. And for the AT Zwitter ion, you can see that basically it just does not contribute to the mutation in DNA, despite the very huge amount of its formation, because it's extremely unstable and it always wants to reverse back irrespective. Okay, so let's just summarize what we found overall for the case of without electric fields. We realized that this is the first study that had statistically and robustly studied all the possible mechanisms. And we had given statistics of each one of them, which one is more probable by how much. This is the first fully realistic model that was built that matched beautifully the NMR results for the kinetics. The stepwise mechanism for the double proton transfer of the GC was a lot more favored than the concerted mechanism. But in both cases, we had the K way less than 1, specifying that the GC wants to go back to its canonical form. The stepwise reaction was a lot faster than the concerted one. After 1 second at equilibrium, we could generate 20 rare tautomers, but only one of them will be contributing to a permanent mutation. And for that AT, we just find that AT star does not want to form at all. The AT star is way less present, in other words, than compared to the GC star, which is in full agreement with the observations experimentally made. The AT Zwitter ion is present 1,000 times more likely than the GC. However, it has a half-life of only 6 femtoseconds, and it very swiftly reverts back to AT. So the AT, therefore, Zwitter ion is likely not to contribute to the point mutation mechanism. So then we wanted to say, now we know what happens in the absence of field. What happens now if I apply an electric field externally and see what happens? The first thing we had to decide on was the range of the fields that we are applying. And here you can see that we decided on 10 to the 8 to 10 to the 9 volts per meter, and those were not random. We calculated these fields to be existent in the middle of a spot between two charges of 0.5 and -0.5 on each side. And the field here, assuming that I have a distance of 10 angstrom, will be 10 to the 9 volts per meter. Assuming the distance is 34 angstrom, it's 10 to the 8. Why 10 and 34 angstroms? Because these are the distances that we found to be relevant for the DNA environment. How do these fields compare with the therapeutic fields that are applied in the literature or even in application? You can see something that's 10 volts per meter is used to enhance or speed up the healing of wounds by almost 25%. 1,000 volts per mole is used for making higher permeability for curing cancer, and that will help the penetration of drugs molecules. Up to 10 to the 5 volts per meter over microseconds is used in electrochemistry. Up to 10 to the 7 volts per meter over only nanoseconds is used in gene therapy via electroporation, so that you allow the DNA to go through the phospholipid bilayer. And This is not in the medicine, but at the scanning tunneling microscope, you can see that's used for imaging, uses electric fields that are greater than 10 to the 9 volts per meter, which is the threshold we cut for our study. Okay, so how did we apply the electric fields? We decided to apply it on 3 different orientations. You can see here it's applied in the X direction orientation, the Y, and the Z. The X is actually parallel to the double proton transfer axis. The Y is perpendicular to it along the DNA. The Z is also perpendicular to it in and out of the plane. And then we applied each of the X, Y, and Z in both directions, the negative and the positive directions. And how did we create or generate this electric field? We had 2 plates, and in each of them, it's 100 by 100 angstrom plates, and they have each of them 100 charges as dummy atoms, and these have values of anywhere from micro to 0.1 atomic units of charges to generate the field strength that we were interested in, starting from way less than 10 to the 8, with 10 to the 4, and even 0 in some cases, all the way to 10 to the 9. What did we find? We found that most importantly that the fields that were perpendicular to the double proton transfer axis made no differences. They just made no differences, not in the kinetics, not in the thermodynamics, nothing that was substantial to report. And therefore, we decided to drop them. So the focus was only on the fields that are parallel to the double proton transfer. Now, we just wanted to make sure that when we are applying the field and we wanted to, here we are applying the field and we wanted to go all the way to the protons here, we wanted to make sure that the field is, by the time it arrives here, is still of the strength that we had set it to be. And for this, we did a homogeneity test. And we looked at the field at the center, and we did plus or minus 20 angstroms. We saw that for the X direction, for the field in the X direction, the electric field value can change up to 10%. For the fields in the Y and Z, it changes up to almost 4.5%. But our region, we are looking at plus or minus 5 angstroms, so we are within this region, and you can see that percent deviation in the value of the electric field is very minimal, and we were happy with this. Now, in the absence of fields, we took 24 replicas and we applied QMMM with the QMMM on 24 replicas. Now we want to do the same, but the question was, can we take the same 24 geometries that we had from the field-free case? And to answer this question, we did MD simulations with strong electric fields applied. And we looked at the RMSD in the geometries. And this is the range of error that we found in the absence of field. And here, all of those are for the fields that are in X, Y, and Z, both plus and minus over all field strength. And you see that all of them have the same range of error. So we were happy with selecting the same 24 geometries that we had chosen in the field-free case, and then run the QMMM simulations in the presence of fields applied on these geometries. If you look here at the hydrogen bond length between the base pairs over the field, how they change with respect to the field strength, you see that up to 10 to the 7 volts per meter, the results are basically just not changing. And therefore, we were confident that with fields up to 10 to the 7 volts per meter, we are happy with the geometries and they will not be changed and there will be no effect on the structural point of view. Now, so we only turned attention now on the very strong electric fields, not the 10 to the 7, we dropped them, we are only looking at the 10 to the 9. You can see here, I'm showing the results in the presence of fields in the X direction, in the X orientation, both directions, minus and positive. And I'm showing you all of these numbers are out of 25. So out of 25 replicas, we found that when we apply the field in the minus X, 17 of them happen to form GC rare tautomers through concerted mechanism. If you remember, the majority of the GCs in the absence of field, the majority happened through stepwise. But that was not the case with the -X. For the +X, you see that the majority of the replicas actually went through single proton transfer to generate the Zwitter ion. So here we see a huge difference, not only between the electric field and non-electric field, but also between the different directions between the plus and the minus directions. So here I'm showing you the energy profiles of all 25 replicas that we did in the presence of the strongest field. And you can see that for each scenario, you have a red line, a black line, and a blue line. So these correspond to the black in the middle is for the zero electric field, the red is for field in the +X, and the -X for the blue. So for all of those, you can consistently notice that the energies, and here I'm talking about the absolute energies, in the -X are greater than those in the no field, are greater than those in the +X. Overall, the +X is stabilizing the whole process a lot more. This was also true not only for the absolute energies, but also for the relative energies when we are taking reaction energies. So you can see that the field in the +X decreased the reaction energy compared to the zero field, but the -X actually increased the delta E compared to the field free case. Here you are seeing in the first line here, all of those things are reported as electronic energies versus everything at the bottom is Gibbs energies. And the first observation is you can see how all of these curves are flattened compared to these curves. And that was already observed earlier where Gibbs is flattening everything. The other thing we notice is the Gibbs energies are reducing the transition state energies by about 2.5 kcal per mole, and they are reducing the reaction energies by up to 0.5 kcal per mole, and they are flattening the curves. Now here, when we look at the G star C star formation and the stepwise mechanism, you realize that for the K equilibrium, it's reversible. It favors the reverse reaction with -X, but it favors the reverse reaction with the +X a lot more. So this is telling you that in the presence of fields in the +X, they want the reaction to be reverted more than in the case of the minus. If we look at the half-lives of the minus, it's greater than the +X. And if we look at both of them, actually, they are in the range of 10 to the -13. They are both greater than the half-lives that we observed in the femtoseconds and the picosecond, 3 picoseconds that we observed for the for the case of no fields. Therefore, out of all of these, we concluded that compared to the field-free case, the GC tautomers are less likely to revert when the fields are applied. In other words, the fields are stabilizing the products and they are less likely to revert back to the GC, and in the absence of field, they want to revert more, keeping the fidelity of the DNA. So here, let's see what happens with the concerted mechanism. For the +X, we did not have any favored reactions happening, but for the -X, it was favored. So the -X favored the concerted double proton transfer, as you can see here. And for the single proton transfer reaction, you can see that the -X had favored no reactions, but the +X favored them. So overall, the field in the +X direction favored the single proton transfer for the formation of the Zwitter ion. So as a quick comparison between both double proton transfers, the concerted and the stepwise versus the single proton transfer, you can see that in both of these cases, the barriers are higher than here. The K equilibrium of the Zwitter ion is greater than the K equilibrium of the rare tautomers, meaning that these will be more favoring the reverse back than this one. And Therefore, we notice that the point mutation is more favored and faster with single proton transfer, mostly as a result of the lower barrier heights, than in the double proton transfer. Okay, what does this mean biologically? Biologically, that means that when we are doing the MD simulations and applying the electric fields, no matter what the field strength it was, even up to the 10 to the 9 volts per meter, we had no significant changes in the structural properties to report. And when we applied the QMMM, we found that fields that are weaker than 10 to the 7 volts per meter did not make any contribution towards the Löwdin mechanism for the formation of permanent point mutations in the DNA, meaning that the thermodynamics and the kinetics were not affected, meaning that if you were to apply these fields in medicinal applications, they are completely safe in the point and perspective of Löwdin mechanism. And here you can see that for the fields that make a difference at all are only the fields that are parallel. Perpendicular ones have no effect. And even when they make changes to the kinetics and thermodynamics, the strongest field, the half-lives of the products that are formed are absolutely small. We're talking about picosecond and femtosecond. They are just not stable. They were only stabilized with fields greater than 3.0 times 10 to the 9. What does this mean? It means in the phospholipid bilayer that where you can find fields up to 10 to the 9 volts per meter, you are just short of stabilizing the rare tautomers, but they will not stabilize them. You are still in the range where they want to revert back. Overall, in conclusion, this study that I presented to you here is a project that for the first time did a robust study to report energies, rates, thermodynamic properties with standard deviations. It was the first study that was of a fully realistic model that showed statistical distribution of which pathway is preferred over the other. We found that only 20 GC base pairs will form in the absence of electric field, but one of these 20 will lead to permanent mutation. 80 star rare tautomer does not want to form. Instead, we are having Zwitter ions formed at a very high concentration levels, but they will not contribute to the point mutations because they had very short half-lives. Fields that are less than 10 to the 7th volts per meter were not significant, and they will not play a role in any mutations. Fields only oriented in the X direction were important in case they were up to the 10 to the 9 volts per meter. With those, the E plus increased the likelihood of the formation and stability of the Zwitter ions, while the minus X increased the likelihood and stability of the G star C star Zwitter ions, both of them compared to the zero field. But even when those are more stabilized and favored compared to the zero field, both of them are very transient species because they have half-lives in the picosecond scale, which still orders of magnitude smaller than the time scale of the DNA replication, which is nanoseconds. And therefore, they are not contributing more to the mutation, even in the presence of these electric fields. With this, I'd like to show you a photo of my team. These people are here at the UAEU. Alex is at UCL. He graduated and he was co-supervised with Peter Kovney. He is the big elephant in the room because all of this work was done with him. And now Anju is taking over with this project to take it further. With this, I'd like to thank the collaborators, Peter Kovney and Sharif Mehta, for contributing to these studies. Thanks to you and Thomas, who helped us with the ChemShell on Archer. And thanks for all of these for the financial support. And I'm happy to answer any questions. Thank you for your attention.
Fantastic. Thank you very much, Alia. Just a quick reminder for the audience, if you do have any questions, then please navigate to the Ask the Staff a Questions panel, which should be accessible via the question mark icon on your screen. There's a picture on the slide here that shows you what it should look like. So then go ahead and type your questions in there so that I can read them out for you. Okay, so whilst you all have some time to gather your thoughts, I just had a few of my own questions for you, Alia. So first of all,
Okay.
as far as I'm aware, the kind of like the technical details of this proton transfer mechanism are very much still debated in the literature. So does this study
That's
suggest
right.
any particular form of the mechanism over any other?
That's absolutely right. So here, even that table, I showed it at the very beginning, but that table also showed it. If I go here, so here, what we did is we did 25 replicas, and we did the nudge elastic band process. So we allowed the reaction to go to whether it wants single proton or double proton transfer, concerted or stepwise. It chose to do its thing. In the literature, there has been a big debate. So some people will say, you will have only single proton transfer. Some people will say, no, you'll have double proton. Even those who report double proton, they say it's going to happen only through concerted. Some of them report stepwise. So the beauty of this study is that we were capable of statistically saying that all of these things actually exist, and we were capable of quantifying which one of them is most probable.
Sure, I see. And so that choice of 25 replicas, was that kind of dictated by computational limitations, or was that kind of like, was that number 25 selected to observe certain statistical?
This is the magical number that we got out of our energy analysis. So you can
Oh,
see
sure.
here, if we do one replica, the error is a lot bigger than 2, than 3, and it kind of stabilized after 24. Ideally, you'd hope that this margin to go to 0, but then you would need hundreds of replicas. So we were very happy with the 24.
Sure. Okay, brilliant. Thank you. And so then another question that I had is concerning the CAM-B3-lip density functional that was used in your comparison. Because from the H-bonded GC results, that density functional seemed to perform pretty well, whereas looking instead at the stacked base pair setting, CAM-B3-lip was quite poor, with the error being several times chemical accuracy, in fact. So yeah, I just wanted to ask you, do you know why that is and why that occurs?
Here. Okay.
Yes,
So
exactly.
you're referring to these high energies.
Exactly, yes.
Yes. Yes. So here, what I am doing is we are doing the benchmark with respect to hydrogen bonding. So we are taking the GC and we are looking at the hydrogen bonds, how well they are reproduced at the scale of geometry and energy. However, in DNA, because we are taking a dodecamer, you cannot neglect these stacked base pairs. And these stacked base pairs have been found to make a huge contribution towards the geometry of the helix. So you have a helix basically because of these interaction, is what the literature suggests. Long story short is that they are extremely important to capture, although they are way weaker energies and a lot more difficult to capture. So here, these are the results of the energy of the errors that we reported for not only the hydrogen bonded systems between this and this, but also for the stacking, which is much smaller and more difficult to capture. And you can see that for the B3-lip, for all these three methods, we have complemented them with the D3 for the dispersion correction. So there are three different variants of accounting for dispersion, which is the weak interactions that I'm talking about here. And in the CAM-B3-lip, it accounts for these dispersion that are long-range interactions by building, it's a built-in function, and it does it by, in the quantum DFT world, we say them a range separated. So for the short range and the long range, and for the long range, it kind of introduces some Hartree-Fock components to them that are just happen to be still not capturing these weak interactions. They're up to 65% mixing with Hartree-Fock at the long range, but they are still not enough to capture these weak interactions. For the B3-lip, it's only in the short range, so you have the 20% contribution from the Hartree-Fock, it doesn't do short range and long range, and therefore these D3 corrections as added terms are doing a lot better of a job than the built-in dispersion in that model.
Right, I see. Okay, I understand. Thank you. So all of these energy errors, is that in relation to the couple cluster energy that you got?
That's right. So with respect to the couple cluster values that we got from Hopsha's group.
Right, I see. Do you know how many, like, roughly how many electrons there are in the system? Like, how difficult is that couple cluster calculation? Do you know?
Oh, they are really difficult. They are really difficult to capture because of computational resources. So here what Hopsha has done is really state of the art, and they need big computational resources to be able to do them. So it's not an easy thing to do at all. I am sorry, I do not happen to know. I never calculated the number of electrons of these ones here. But 1, 2, 3, 6, 7, and 7. So if you have 20 atoms here, and each of them is 10 electrons, let's say roughly, so you are around 200 electrons. I'm just estimating quickly.
Sure, yeah, and what I mean, this was including triple excitations, was it? The couple cluster calculation.
That's correct, because yes, well, actually they are doing more than triple, because they are the way Hopsha's group account for the complete basis set limit is they extrapolate with as big basis sets as possible. So in some cases you see they use quadruple and quintuple basis sets to do the Hellkegger or other schemes of extrapolation.
Wow, okay. Yeah, this is the thing, is because I'm from the world of quantum computing, and so the sorts of systems that we can look at in that world are pathetically small in comparison. So it pales at the thought of a system of that sort of size. But no, thank you very much for your answers. I'm not actually seeing any questions coming in from the audience. Oh, actually, just as I say that, I think one has just come in. I don't know the name of this, but whoever sent this question in, but they say, thank you very much for this presentation. I found it very informative. I did have a question, please. So Dr. Arabi mentioned, when looking at no external field impact, that it works the same for AT. I'm having trouble understanding how the model, assuming they're using the same equations, is applicable to study the effects of electric field on the weaker double hydrogen bonds of AT pairs or stretches.
That the methods that we have used, especially for the QM modeling, are methods that capture even weaker than hydrogen bonds. So although AT can be hydrogen bonds in the AT are weaker than in the GC, we have even weaker interactions, which are here the dispersion interactions, and our model is capturing even these interactions. So we have absolute no problem with capturing the weaker AT hydrogen bonds, given that we can capture the even further weaker dispersion interactions. I really hope that answers the question. If not, I'll be more than happy to reiterate if the question is written differently.
Super, thank you, Alia. We've got another question coming in here as well. So this is from Matteo Mascagni. So they were wondering if something is missing, e.g. in the research infrastructure, financial instruments, training, etc., in order to further support these kinds of research activities.
We did have lots of limitations, yes, because originally and this is why we started originally with smaller base, we took the isolated base pairs until we were capable of scaling up to the QMMM realistic model. And at the time when I was working on these projects, I was at Zayed University, and there I didn't have infrastructure of computing resources at all. So the only way I could do some of the calculations was because we were associate partner of the CompBioMed project, and because I collaborated with Professor Peter Kovney. You can see even in the acknowledgement at the end, I am thanking here. I'm thanking all of these people with the collaboration, because through the CompBioMed we were capable of accessing the Archer, which otherwise it would be really difficult to have access to any machines that can digest all of these simulations. These are not computationally easy or they are extremely intensive calculations with double zeta, QMMM replications 24 times at each electric field. They are extremely intensive. So if it wasn't for the access of the computer resources through CompBioMed, we couldn't have done it back then. But now at the UAEU, we have managed to build our own resources from separate grants, and we are kind of very independent in that sense, and we are capable of reproducing these things within the facilities that we have here locally.
Super, thank you. One thing that I
should say the other challenge also we faced is when we did this.
Sorry, yeah, you continue, Alia. I think there must be a delay.
Difficulty was, so at the time when I completed the project, I was still at another institute that's mostly undergraduate oriented. We did not have a graduate program. So the human resources in that sense also was a challenge for us for the project. And if it wasn't for this collaboration also at that time, we wouldn't have had the student who is Alex and now graduated to do the study. With Sharif Matta, I was actually the student myself completing the simulations, but that was long ago when we started with only the formic acid dimer and the QM excluded regions exclusively. But now also at the UAEU, I am in a program where we do have graduate programs, and I am at the university, and you can see that I am living ever happily with this team. We are called the vibrant team because you can see they are always vibrant with happiness.
That's an excellent name. Thank you. Just to say that the people who ask questions, Alia, they both say that your responses covered the questions for them. So thank you very much for that. It doesn't look as though any more questions are coming in, so I think this is a good point to draw the session to a close. So just before we end, I'd just like to take a quick moment to plug CompBioMed's free scalability service. So if you're someone who uses or even develops biomedical applications that necessitate intensive computation, but you are running into performance issues that are limiting the scope of your research, then CompBioMed offers a service that's completely free of charge to improve the turnaround of your computing jobs. And so Alia, if you wouldn't mind going over to the next slide, please, for that.
Oops.
Super, thank you very much. And then maybe the next one as well, please. I think there must be a delay between me speaking and you hearing what I'm saying. But if this is something that applies to you and your research, then you can fill out an application form available on the webpage displayed at the top of this screen. Or you can also you can reach out at the email address shown here or via the InSilico World Slack channel as well. Next slide, please, Alia. So InSilico World is a community devoted exclusively to in silico medicine, offering expertise, opportunities for collaboration, and a safe space to exchange ideas and advice. Next page, please. And already InSilico World has a large following, including members from large biomedical companies, biomedical SMEs, independent software vendors, clinical research institutions, and even regulatory and standardization bodies such as the FDA and NICE. So that's everything I wanted to say on that. Thank you once again, Alia, for giving us your time today. A reminder, this e-seminar will be available on the CompBioMed YouTube channel and website, which is accessible via the link shown on, well, sorry, it was shown on a few slides back, it was shown. But finally, thank you to everyone in the audience for attending, and I hope that you all enjoy the rest of your day.
Thank you so much, Tim.
Not at all. Thank you, Alia.